Thanks a lot, Marco, for this long introduction, and I'm very grateful. So, indeed, so hi to everyone. So I will be talking today about my activities on nanofluidic transport. So mostly the fundamental activities that we perform in the team. So but our team is actually working on various topics, but basically the bottom line is that we are looking at fluids at interfaces. So we are a small team with one chargé de recherche, Alessandro Siria, with whom I've been working for more than 10 years now, and Antoine Niguès, who is an engineer who joined us 3 years ago. And so we are working on various topics, whereas basically we look at how interfaces couples to transport in the bulk, from the metascales, where we did a lot of studies actually on ice and ice friction, and actually it was a very funny topics in collaboration with Martin Fourcade. And but today actually I will be mostly discussing. Oops, my stuff is not working. Okay. Today, so I will be mostly discussing the very strong confinement aspect of this. So actually, I like this quote from Pauli, who said that God made the bulk and surfaces were invented by the devil. So this is extremely true. And whenever you do any experiments with surfaces, it's always a nightmare. But I like to say that probably the devil side is more interesting than more standard God side. So that's what I would like to discuss today. And also, what is interesting is that, okay, nanofluidics is a study, it's a domain which emerged, something like 10 years, 15 years ago. It embraces the transport of fluids at the nanoscales. And what is very interesting right now is that now we can build we can build systems that we were only dreaming of something like 10 years ago. So now we can look at transport across nanotubes, and this I will explain to you in the seminar. Nanopores, so you can drill holes of a few nanometers in membranes. So this is MOS2, actually these membranes. And more recently, there were a lot of advances from the group of Andre Geim in Manchester, where he showed that it is possible to actually make slits where the confinement is of the order of 3 to 7 to 1 nanometer, 7 angstroms, sorry, up to a few nanometers. So that's a great advance. So meaning that you can really probe the limits of basically the flow, and everything that you know about flow here is very different. Now, the second point is that now it's not only that you can make this device, but you can also probe the flow and the whatever flows inside this. And this, I will show you that this is not so obvious, to make measurements in this system, but now we can do it. And last but not least, and this is in some sense what motivates us, is that indeed, when you look at the transport there, you find some, let's say, exotic transport, in the sense that you find things which you do not expect. And because this just means that this is worth the effort to make all these steps. And actually, another interesting aspect of nanofluidics, and actually Marco mentioned it, is that it's very interesting because it's very close to very important topics about water purification, also energy. Because this is simple to understand, because for example, if you look at desalination, where you want to take out salt from water, basically you need a membrane across which the water will pass, but not the salt, so hydrated salt. So meaning that you need a pore size in the range of a few angstroms, and for sure the flow there is very different from everything that you know usually. So if you can do advances on the nanoscale flow, you can do advances on membrane transport and etc., and go beyond the standard views of sieving. Right now, basically all these domains of desalination, etc., is based on very standard views of, okay, either big things do not pass and small things pass. But I think you can go much beyond these aspects. And to illustrate that, I like to come back to my favorite cartoon. So probably in this assembly, probably the younger do not know the Shadows, but that was one of the cartoons when I was quite young. And basically they are quite crazy beasts. And actually there is a full episode on the logic of the sieve, la logique des passoires. And basically they explain in very detail. So that's very well done. That actually, okay, if you want to separate spaghetti from water, you just need a passoire, a sieve. such that the holes are, let's say, smaller than the size of the spaghetti. Very fine. This is very much like DNA translocation, what they explain. But of course, these are crazy beasts, and they invented they say a third order complex colander where only the spaghetti goes through and not water, because water is just large, much larger than the holes, which of course makes no sense. But actually, when you think to it, this is exactly what we want to do. And actually, and also we did already this kind of stuff where large molecules pass, but not the small ones, for example, I mean, using some specific nanofluidic effects. And so this is what motivates us in some sense when you go beyond the fundamental aspects, that you know we have new materials like graphene, boron nitride, MOS2, and new systems, and we see new behavior, and you can really use this to make this kind of strange colander, strange effect for water separation, filtration, remediation, etc. And we did that. We do that already, indeed. Okay, so on these topics, actually, I've been working mostly with Alessandro Siria since 2009. So what I will discuss today is basically these 10 years of work, lately with Antoine. And we have been working on various topics. So ionic transport, so our ions go through the nanotubes, and application to blue energy, which I will not discuss actually today. We have been working a lot on mass transport, so of water flows across the single nanotubes, and this is exactly what I will discuss in these topics. And more lately, with in collaboration with André Geim and Rada Boya, we looked at the transport across these extremely thin layers of a few angstroms in thickness, where you start to see very strange transport in these systems. So this was a really 10, I mean, quite exciting years, quite difficult, I would say, because these experiments were mostly failure. I mean, you go from failure to failure, as you know, but, here, I think that's, now we have made a lot of progress, but what I always like to say is that, okay, you can do all these kind of systems, but we are still very, very far away from what happens in nature. For example, in nature, you have things like these aquaporins, which are filter for water that you have in your kidneys, and they are ultra fast, ultra selective. This would be a kind of ultimate membrane for desalination. And right now, we do not know how to reproduce this behavior. And also in nature, you have plenty of active systems. So from ion pumps, where you pump ions from one side to the other side of a membrane. And I mean, right now, we do not know how to make that. And also you have some more advanced systems like this, here I quote, mechano-sensitive channels, where basically
Lydéric,
yes?
excuse-moi, on voit que la première slide, c'est normal ou tu es en train de défiler?
Ah non, non, ouais, ça va pas du tout, non.
Ah, bah voilà, parce que...
Okay, sorry, because you didn't see this?
Not really.
Vous avez rien vu du tout, ok. Ok. Non, bon, bah, je suis désolé, je sais pas ce qui s'est passé, parce que moi je le voyais... So, est-ce que vous voyez là, par exemple?
Oui, oui, là on voit.
Bon, c'est un bug qui s'est passé. Okay, sorry for this. I mean, I was basically explaining all this. So, okay, I will skip all that. So, I mean, you heard the topics. Now you see the drawing. So, so what I just said a few minutes ago is that we did all these various systems where we, over the last 10 years, we are building nanotubes. So if you can see this, and look at transport across nanotubes, and this I will talk in the remaining of.
Alors là, on est toujours sur les shadows.
Ok, il y a un problème à ce moment-là avec le partage. Je sais pas ce qui se passe. Okay, je vais laisser ça, si ça vous va.
Okay.
Ouais.
Là, vous voyez.
Ok, oui, oui.
Bon, je sais pas ce qui se passe. C'est la première fois que ça me fait ça. Ok, ça va être compliqué quand même, mais bon. Okay, so what I will, what I wanted to say is that basically you have, I was on this here on this slide, so discussing that actually you have extremely advanced functionalities in nature, and you can do active membrane, you can do stimulated transport. So I was discussing these mechano-sensitive channels where basically you under a stimuli, so typically a force, you can modulate the ionic transport, and this is used for as a sense of touch and a sense of proprioception, or you are in space. And this typically we do not know how to make all this. So this is what, and one aspect of our work is to really to understand, I mean, and try to build these systems simply using the nanoscale transports that we are studying. So this was a long introduction, and I'm sorry for this mess with sharing the screen, but this to say that there are some interesting science to be done there. And here, one thing I would like to discuss a bit more exhaustively is a transport across carbon nanosystems. And indeed, as Marco was saying before, I was using this fast and curious quote for carbon, because carbon in, okay, you know carbon as graphene for electronic transport and etc. But in for water, I mean, for water transport, it's also a very weird materials, and you have plenty of publications where people report very fast transport of water across nanotubes and also across graphene. And basically, we do not really understand why. And this is what I would like to discuss now. So here I'm discussing the friction of water on graphene or graphite and etc. And so in fluid mechanics, we usually introduce what is called a slip boundary condition, because basically you have some, if water flows, maybe it will not stick to the surface as is usually expected, but may have a slip velocity. And actually this slip velocity introduces a partial slip velocity, boundary condition, which I show here. But what is important is that it is characterized by the length, which is B, the slip length, which is an extrapolation length. Let's say you have a slippage and you extrapolate to 0 inside the system. So, but the physical quantity is a friction coefficient, which I show here in this formula. Slip length equal to viscosity of the fluid divided by the friction coefficient. So if you have a large slip length, this means that you have a low friction. And actually, if you look at transport of, let's say, water inside a nanotube or inside the slits, actually, whenever you have low friction, so slippage, then the permeability, so the permeability is how much the system flows under pressure drop, is strongly enhanced by this slippage. So really, here, the question is how, I mean, this various paper, which reports very high flow, means that you have low friction of carbon. And when I say low, it's extremely low, because, for example, here this was a paper it was a paper about flow across a membrane, so a very large membrane of carbon nanotubes, and they reported slip lengths in the range of up to microns, basically. And just, I mean, of course, it doesn't mean much to you, but just to give you a comparison, a typical slip length in a very carefully prepared flat and hydrophobic surface is at most a few nanometers, let's say 20 nanometers at most. So here, right here, you have 1 micron. So it's orders of magnitude, meaning that carbon or graphite or graphene, so I will come back to that, apparently has a much smaller friction as compared to any other material. And this is what we wanted to understand. But since all these measurements were done on large scale membrane, we wanted to study first what happens in single nanotubes, because this is, I mean, just like in electronics, I mean, it's better to control everything that you have. So we wanted to make experiments in single nanotubes for a better understanding. And another advantage that we could is that we could look at material effects. So because in particular carbon nanotubes, obviously, but there are also boron nitride nanotube. And as you know, boron and nitride are the neighbors of carbon in the periodic table. And something which is extremely interesting is that boron nitride has basically exactly the same crystallography as carbon. I mean, close to, I mean, not exactly, but very close to. But it has very different electronic properties. So let's say carbon is, say, semi-metallic, let's say, and boron nitride is strongly insulating with a gap of a few electron volts. So for us, it was very interesting, because if we see any difference between the two, this means that this should go to the electronic properties. Okay, so now how to fabricate this system, and this is what we did with Alessandro and what took quite long to develop. So basically we use like Lego. So what we do, and maybe I should show immediately you a movie. So here, this is a movie of what happens is that you have, basically you do experiments in electronic microscope, and you grab a nanotube in a powder, and then you can manipulate these nanotubes live. I will repeat the movie, yeah, oops. You can manipulate the nanotube live using step motors with nanometric sensitivity. And then you have a membrane or whatever you have in front, in which you dig a small hole of 100 to 200 nanometers. And then on live, you can introduce a nanotube inside this hole. And then we have developed a full, let's say, workshop where we can glue, as you will see the second in this movie. Close to the hole, you will see some glue arriving here. And this glue is done by cracking some gas, etc. And then you can retract, you can cut. So we have a full, let's say, workshop where we can introduce carbon and boron nitride. And at the end of the day, what you have is a single nanotubes embedded in a membrane. So you do not see the membrane on this picture. You see the big glue here. See here, it's a quite large nanotube, I think 15 nanometers diameter. But or you can insert a nanotube at the end of a nanopipette, as shown on this other graph here. And in the end, you have this membrane, and you sandwich the membrane between two big reservoirs, as shown here. And then you fill the reservoirs with water, and then you can apply voltage, concentration, drop, or pressure, and measure the transport across these nanotubes. And okay, so we did this. I mean, what is easier is to measure ionic currents. But now I would like to show you more about this permeability. I mean, how do you measure friction and slippage? And okay, so maybe I will show you the animation. So how do you, I hope you see, and in case you don't see, please Marco, tell me. So I would like to measure the permeability. So this coefficient, which measure basically how much flow of water you have under a pressure drop. And if the problem is that the flow is extremely small, I mean, if you put orders of magnitude and quite optimistic ones, you will have femtoliters per second at most. And right now we have no method to measure flow of water at this level. I mean, typically at most we can do picoliters per second. So, so here, what we actually the trick to bypass that is to measure a force. So let's say, you know, I mean, this Karcher like of stuff, when, okay, you induce a jet, and this jet can push some dirt on the ground. So basically, this is exactly what we do. So we have a nanotube, so we have a nanojet. So you apply some pressure, so you induce a jet, and this jet will move some Stein, which are small colloids, which is contained in a reservoir, which is around that. And the key point is that this flow of water is characterized by a force, which is the force transmitted by the jet, the nanojet inside the liquid. And this makes a huge difference, because what you measure in this measure here is a force and not a flux. And this is really a singularity of this special flow, which is called actually the Landau square flow. And the reason for that, you can understand from the scaling, is that at this scale, so here we are talking about nanoscales, the force is of viscous origin. So if the force is of viscous origin, then it should scale more or less like the viscosity of the fluid outside here, the radius of the tube, and the flow coming out from the tube. So that's just scaling, dimensionality. Now, if you measure a flux, so how much water goes through, this flux will be the velocity of the tube times the area of the tube, so r squared. And then you see immediately that when the radius goes to 0, this coefficient, this case like r to the 1, r to the 2, this will be much larger than this one. So you can still measure force, while the flux, basically you cannot measure it. So this is how we do actually in this experiment. So in practice, we do the same workshop tricks as before. We insert a nanotube at the end of a nanopipette, so a Pasteur pipette. And here you see just after insertion of a given nanotube, this is another nanotube here. And this nanopipette, you embed this in a big reservoir where you put some colloids just to highlight the flow, and you push with pressure. And here on this graph down right, I show you here trajectories, individual trajectories of colloids. So let's say Stein particles inside the fluid. So you see exactly this flow here, and just like the prediction of Landau and Squire, I mean this here. And but what is key is that here the nanotube is of the order of nanometers, but you see flow in the range of microns. And of course, if it's micron, you can measure it. And this means that you really make this, let's say, bridge the gap, as we used to say, between the nanoscale, where you cannot see anything and you cannot measure anything, and the microscale, where you can do measurements. And so this is just, for example, this figure here on the right is just to highlight that we indeed see, I mean, whenever you increase the pressure, here is a accumulation of trajectories. You see, I mean, that the larger the pressure, the larger the flow. So now I will skip a full part of the study, which took us actually something like 1 year to complete, where, I mean, from this graph and these plots, you can infer the force. So that's quite immediate. I mean, you analyze the flow in details. And then from this force, you analyze the flow velocity inside the nanotube. So here I write approximately equal, but actually you have it's equal and a prefactor. And it took us something like, I was saying 1 year to fully benchmark this prefactor, but actually it happens that in the end, the prefactor is basically 1. So which was a bit deceiving, but at least we know that it's, we could benchmark it very carefully. So once you know the force that you measure, and you impose the pressure, you can deduce the permeability. And from this permeability, you can do this for various carbon nanotubes, boron nitride nanotubes, and you get this kind of plot here. So this is the outcome of all these measurements, where you have the permeability of nanotubes as a function of their radius. And here you see we look at quite large radius of nanotube from this is 15 nanometers up to 50 nanometers. Actually, we cannot, using this technology, we cannot go below in terms of radius because we cannot measure it simply. It's not sensitive enough. But already we found there was a big surprise there that first you see a huge difference between carbon and boron nitride. Actually, this boron nitride, and this is interesting, the permeability here is dimensionalized by the no slip prediction. No slip means that you have no slip here. The velocity profile in the tube is something like that.
Vous avez dit pas d'emmaillotage sans notre surveillance, mais
quelqu'un devrait couper le micro, s'il vous plaît.
Pardon, je croyais que c'était une question. Sorry. So here, this is the no slip boundary condition prediction, and actually for boron nitride, this is exactly what we measure. The dash line, the red dash line here is 1. So here you really measure precisely no slip boundary condition. So high friction on boron nitride, but for carbon, you see the permeability is up to here in this over this window. It's up to 25 times the no slip prediction. So you have a low slippage as we expect. Actually, you can translate this in terms of slip length, and I told you that the slip length is a quantity which quantifies water friction. So slip length is basically 1 over water friction, and actually you find that you have no slip on boron nitride and huge slippage on carbon, as large scale membranes showed. But something, so you see here for carbon, something which is weird is that you see a very strong increase of slippage. So it says the friction decreases very strongly when you reduce the diameter of the carbon. And this actually echoes something that we predicted with my friend Roland Netz a few years ago, actually, where we had also a kind of a theory and some simulations there to show that the slip length in carbon nanotube indeed should increase when decreasing the radius. And this was the predictions there, where it was a question of commensurability of the water structure and the graphene structure, let's say, of the confining carbon structure. But actually, so that is nice. I mean, qualitatively, you see, okay, you have an increase when you decrease the radius. You have the same here for the prediction and the simulation data. But you see here in the theory, you see an increase below 2 nanometers. It's really a molecular effect that you see here in the theory. And here you see an increase already for 40 nanometers. So, and the effect is much stronger in the experiments as compared to this theory. So this theory is okay, but I mean, it does not work at all in the end. So that's, I will come back to this later. So, I mean, to say a few things about this, to conclude, to summarize a bit, I mean, I think and I will come back at the end of my talk here. What we can say here is that it's really a system where you start to see quantum effects on hydrodynamics. You start to see that first boron nitride is different from carbon, but also that carbon, the effect of friction on carbon, you cannot quantify it by simple classical elements. And you need to go to electronic friction and ab initio simulation, and it's still not understood. And I will come back to that. So, but before I come back to that, I would like to say a few things about nonlinear effects. And these are the more recent experiments that we did. Marco, don't hesitate to tell me how much time I still have. I mean,
still have time. Don't worry.
Okay. Okay. So I wanted to discuss a bit nonlinear transport because I told you that in the end, the ultimate goal is to fabricate, let's say, small systems, a bit like the ionic pumps, a bit like whatever is mimic whatever is in the body. But there you need nonlinear transport. And what we want to do is iontronics, like what is well known for electronics. And actually, something which is interesting, which was put forward recently, is that actually there are a lot of very strange behavior which occurs below 10 nanometers. That's typically, so there was a review paper last year from colleagues from the US, which gathered a number of anomalies which occur in this range. Anomalies in terms of thermodynamics, hydrodynamics, dielectrics, actually. And here, I would like to show that actually, this is indeed a region where it's very interesting to go to highlight this nonlinear behavior. So in the lab, we did various experiments with systems in this range of size, so below 10 nanometers. So previously, actually, we were limited to nanotubes above 10 nanometers in size, but lately we did an effort to go down to 2 nanometers. And so we had to advance our manipulation techniques, and this is what, in particular, Alessandro and Antoine did a lot around that. So we looked at nanotubes, transport across nanotubes with 2 nanometers in size, and then I mentioned to you this work with the group of André Gaim and Radaboya, where basically there you are below 1 nanometer, so down to 7 angstrom, and there you see a lot of anomalies, which I will discuss in a minute. So but here I will focus more on this 1D system, let's say, so these small nanotubes. And okay, first I will show you the linear response before tackling the nonlinear, just to show you how it differs. So actually linear is a bit boring in some sense. So you measure current versus voltage, and at low voltage, let's say, so 50 millivolts, you see standard response. And this depends. So this is a ionic current across a nanotube. You see high conductance, that's fine, but okay, nothing fancy. Something which maybe you are less used to, an interesting response with this ionic transport is to impose a pressure drop and measure a current. And this is not, obviously you cannot do that in electronic systems because you don't have this mechanical driving force at play. But basically what happens is that whenever you create a flow inside the system, this flow will carry on some ions. And if you are able to separate the ions, for example, let's say the minus go faster than the plus or whatever like that, then you create an ionic current. And then we measure what is called the electroosmotic mobility. And okay, we measure that. It's also boring in the sense that, okay, the current is linear in pressure, as you would predict from a linear response. Now, something which hints that something where occurs already is that this slope, so this electronic mobility, actually is something like 2 orders or 3 orders of magnitude larger than anything you could do on larger systems. So this electroosmotic mobility, when you compare it to standard glass, it's 1,000 times larger. So extremely large on these carbon nanotubes, very tiny carbon nanotubes. So you see already that something is weird. But now, what we wanted to do, so of course, this occurred incidentally. You impose delta P, you impose delta V. At some point, you forget to take out the voltage, and something weird occurs. So you have the combined response of pressure and voltage. So, and actually, so this is Alice Marcotte who did these experiments. So when she did experiments of this is a current that she's measuring under a fixed voltage, and then she varies the pressure. And so you have the baseline here, and then at some point you put minus something in pressure. Okay, you have this response, -2, okay. But then you have plus something for the pressure, and you get the same signal as minus. So that's weird. And also plus, and you say you get the same. So, and symmetric, actually, if you reverse the potential. So, if you plot the current that you measure versus pressure, you have something like parabolas, I mean, perfect parabolas. And this, the sign of the parabolas depends on the voltage drop. So you have something in the end, you have something like that. That's you have a current scaling the pressure to the square and a coefficient which inverse with the voltage. And so this, honestly, this was very astonishing to us because honestly, I thought there was some mistake in the experiment first. But actually first, I mean, thinking to it, it's interesting because of course, I tell you that it's linear in voltage, quadratic in pressure. You can reverse that. And actually, you can simply say, okay, in the end, what you have is a gated conductance. So what happens here is that the conductance of the nanotubes is gated by the pressure. So let's say you have a current versus voltage, which is linear, but you can increase it strongly by increasing the pressure. And strongly means you see you have 40% of increase here, which is very large. So I will then to understand that I will not discuss the theory at length. I just want to tell you what is the origin of that. So first, there is, in the end, it's not that a fancy effect. So meaning in the sense that you can account for that by the coupling between diffusion of ions inside the nanotube with flow, actually. The key point here is the flow. So because usually at these length scales, diffusion is always much faster than the flow. And this is quantified by what is called the Peclet number. Peclet number just compares the flow to the diffusion coefficient, and diffusion is always fast at small scales. But here it happens that since the nanotubes have very low friction, the flow wins, and the Peclet number is very large. And actually, then if knowing that the Peclet number is very large, what you do is flushing. Basically, you flush the ions inside the nanotube. So it's a quite standard effect. And you can even do some prediction and predicts explicitly this response of the systems, where the conductance increase quadratically with pressure. And what is interesting here is that you have a mechanical gating due to a friction effect. So it's a bit like a kind of a transistor, a mechanical transistor is a system but gated by pressure and not by a gate voltage somewhere. And a last comment I wanted to do is that actually we also found similar effects in these 2D systems. So this was the work by Timothée Moutarde with that we did with the group of GAIM. Actually, what is funny is that the 2D systems, the gating is reversed. There, you find a linear response in pressure, but sometimes a nonlinear response in voltage. So that's reverse as compared to what we found for 1D. And actually, we could explain this two behavior by the same model, but the only difference is that you have very low friction on 1D nanotubes, intermediate friction on graphite, and high friction on boron nitride. So you see, in the end, you have a full manifold of nonlinear behavior, which is just triggered by the difference in friction on the surface. And so meaning that's becoming a key factor. So, I mean, in some sense, it was interesting to see and understand. What I just wanted to quote is that at the end, it's interesting actually as an effect, because I mentioned to you these mechano-sensitive systems, these channels which react to pressure drop in the body. So they are called TRAC or TREC, which were discovered 10 years ago, basically. And actually this system, so this is from Pina's paper, this system exactly has this kind of response, that the current scales like the pressure. This is the pressure here, it's pressure to the square actually. And this is positive and negative pressure. So it's quadratic in pressure. And here we have exactly the same response. So I'm careful, I will not say that the mechanism that we see here is the same which apply in these channel systems. So typically in biological channels, they have in mind something more like a opening of the membrane channel under stretching, basically. Okay, this has not been really proved actually, but my point is that now we know how to reproduce that, and we can start thinking of embedding our nanotubes inside a larger system. So for example, we have in mind to put nanotubes inside membranes, and then you have a very local and very highly performing stress sensor and pressure sensor in the systems. So right now, I mean, okay, that's for the future, but I just wanted to say that in our quest to make these systems, this is an asset. Okay, so now in the last 10 minutes or so, maybe a bit more, I wanted to go beyond, because I told you that up to now, we are able to control the transport in tiny nanotubes. You start to see non-linearities, which are a bit weird, but at least we understand it. We understand these non-linearities in terms of, let's say, standard mean field description, where it's basically a competition between diffusion and flushing, and we can explain this in simple words, more or less. But we wanted to go beyond and see whether we can obtain more advanced transport. And in particular, I was fascinated by this Coulomb blockade phenomena. And obviously Coulomb blockade, as you know, it's a quantum behavior, purely which you can see in electronic systems, where basically you have single charge conduction across a quantum dot, and you can gate the transport by a gate voltage. And a key signature of that is that the conductance has, let's say, not resonance, but I mean, you have on and off conductance for specific values of the gate voltage. So, and okay, so that's I mean, something quite canonical in electronic transport. But then we were asking, could we see the same in classical systems? And of course, there are many reasons why you should not see that. Because first, we are a priori here, we are mostly non-quantum. We also work at room temperature, so it's not 4 Kelvin, it's 300 kelvins. And also a specificity of ionic transport is that you have plus and minus ions. So meaning instead of purely minus electrons, and this plus and minus leads to electrostatic screening. So whenever you have an ion somewhere, you have a cloud of counter ions around, which screens the interaction. So that's should kill in some sense the Ionic Coulomb blockade. But a great something which is very interesting is that, and I will show you this in a minute, is that in strong confinement you have actually very strong electrostatic interaction, which are much larger than KBT, and this means that you have this strong correlation, could lead in the end, and I will lead in the end to this similar effect as Coulomb blockade. And actually, I wanted to mention that experimentally there was some claim of Coulomb blockade in ionic systems. So, for example, from Alexandra Radenovic in MOS2 nanopores in MOS2. So you see a very, very tiny hole in a MOS2 membrane, and she says, okay, she has current versus voltage, which looks a bit like what you would see for Coulomb blockade. It's clearly not obvious whether this is true or not. Okay, there are some simulations which predict that, which actually see this kind of effects, but I will show our simulation in a minute. So with Nikita Kavokin, so Nikita is a PhD with me, and so we wanted to tackle that. So actually the first thing we did, to be honest, it's not the first thing, it's the second thing that we did, was to do simulations, because when you do simulation, at some point we didn't understand anymore what we are doing. So we said, okay, let's put in a simulation all the ingredients and see what you get. And so to do simulations, what is interesting is that you have a nanotube and you have ions here mostly diffusing in 1D. So the nanotube is of the order of below 1 nanometer, let's say, and you put a gate voltage. So in practice, we put a gate charge because it's easier for theoretical analysis. And then one important aspect is that the interaction in this ionic system, since you have a dielectric contrast between the water and outside, typically, let's say, vacuum or whatever membrane is here, you have a strong at short distance, you have a strong confinement of the electric streamline. So at short distance, the interaction is basically 1D, and the electric field is constant. So, and this is the key, because this is what imposes the very strong correlation between the ions. Now, of course, you have dielectric leakage for larger distance, and then at beyond a distance which is only a distance characterized by the cutoff distance given by the dielectric contrast, you have a leakage, and then you have an exponential decay of the interactions. But this exponential decay is not screening; it's purely dielectric. So now you can do simulations. Okay, one is it's easy simulations for, and then you measure the current versus, for example, an electric field. And indeed, you see depending on the charge here, you find in some case a current versus electric field which is strongly nonlinear like that, 0 at so non-conducting and then conducting above an electric field. And when you plot the current for a given electric field versus the surface charge, so the gate charge, you see indeed this quantized transport. Just like what I told you for the electronic Coulomb blockade before. So, but here nothing is quantum. Everything is classical. So, then you need to understand where it comes from. And what is funny is that it comes from a purely physical chemistry problem. And this is called the Wien effect, which was actually discussed a long time ago, nearly 1 century ago by Larsen Sager. So, but it was discussed in the bulk, and here we discuss it in the system. So what happens, and I will show you in a second, is that in these very strongly confined systems, the ions tend to form pairs. So because let's say if you take sodium chloride and if you put it in a reservoir, we call it a strong electrolyte because the two ions separate, because entropy wins. But here, since you are confined and the electric field is very strong and confined between inside the nanotube at short distance, then there is a very strong interaction. And then the strong electrolyte becomes weak, meaning that you have a lot of pairs like that, neutral pairs and tightly bound pairs. And these pairs, of course, are not conducting. So, and this, here I show you just with a very few ions to highlight what happens. What happens is that, okay, let me first, maybe I will stop the movie. Look at this here. Here I have the gate charge. And on the gate charge, for example, here I have 2 minus charge. And of course, if I have 2 minus, the system will like to compensate this minus charge by positive charge. Then everybody is happy with his neighbor, with his friend. And basically, whenever you apply an electric field, you have no conduction. Now, if you put a fractional charge here, so here I think of fractional charge, but of course it's a fractional gate voltage in practice. If you put a fractional charge, everybody's happy except this one because it's partly bound, and you see that the energy to take away this ion from this half charge will be smaller than for a full charge, and this is what you see here. So, for example, here you have 1.5 charge, and you see that the systems basically hesitate to whether it should leave a charge, 2 charge, or no charge. But then whenever you have impose an electric field, you see that you have a free electron. Then you see exchange, and this one under electric moves, and you see something which is called like the Grotius mechanism, but here for ions inside the pairs. So this is exactly what happens. And now, once we understood that, so then Nikita revised completely the theory. The nice thing is that you can do a fully analytical theory there, because you can solve the Hamiltonian exactly, quantify the canonical partition function using a standard theory of Coulomb gas, except that here we have a gate. And in the end, these red lines are the predictions actually here. So you see it works absolutely perfectly with the simulations that we had before. And you see indeed at the end, the current versus electric first as non-passing and passing, so non-conducting and conducting systems. You conduct over minimal electric field. And also now for a given electric field, sometimes you have no current, sometimes you have strong currents. And this depends, of course, on the fractional charge. So that's why we call it a fractional Wien effect. So for us, it's interesting. It's very interesting because now we see where to look at for this Ionic Coulomb blockade. We know all the parameters, and we see that we can, chase for this system and Biron pairing inside in our nanotubes, and also the 2D slits. Okay, so I will not expand more further, but we have a full phase diagram to that, to prototype the experiments that we are ongoing now. So we did this into 1D, and also recently Paul Robin, PhD student, did it in 2 dimensions with Nikita, and there are some more surprises that I will come later. But why I wanted to tell you that is that actually what we had in mind with this ionic current is actually an ionic pump, because for example, for electrons, these two you can put 2 of these gates in a row. So use this Coulomb blockade effect to induce a pump of electrons without voltage. So you just shift the 2 phases of the gates. And this is exactly what we have done here. I mean, so let's say you can really make a pump where you gate the local voltage on the surface, and gating the surface without an electric field. Now you can pump, and indeed this works very efficiently, where you can pump 1 ion, 2 ions, etc., etc. So you can really do single ion pumping a priori. So this is a prediction of these calculations. So if I come back to this diagrams, this picture that show you before, that indeed we start to see that the nanotubes are flowing a bit like aquaporine, so they're flowing extremely fast, that we know more or less how to do ion pumps. Okay, so right now we still have to exhibit this experimentally, and we're working on this. We know how to do and where to look. We also do some strange mechanical sensitive systems. So at some point we start to gather, let's say, building blocks that at some point we will gather in the future. So with this, I mean, this was a short panorama of what we wanted to do. And maybe I should show the movie here, that as I told you, we want to, this really should be, I consider this as building blocks actually, but now we want to go beyond and build these systems. And something which is extremely interesting is that you know, the brain is not like a computer. I mean, and basically, artificial intelligence is very nice, but okay, it consumes tens of kilowatts to make anything. But and you know, our brain uses 2 bananas per day, and we do quite nice things with only 2 bananas a day. And so, I mean, the brain has, of course, a structure to make calculations which has nothing to do with the computer. And this is done because of the specific way the neural architecture is built. And actually, one key aspect for neuronal calculation is and one key dream is to build memory stores. So basically, the idea is that you build resistors in which memory is encoded. And if you know how to do that, you can do plenty of things which are beyond the simple von Neumann structure of a computer. And actually, what is very nice results from Paul Robin and Nikita recently is that, okay, again, this is prediction, but we looked at the same effects as I was discussing before with the Ionic Coulomb blockade, but in 2 dimensions. And actually, it happens that in 2 dimensions, we found that the system behave as a memory store, actually. So these 2-dimensional slits have a memory, and this memory store actually is encoded in this, oops, sorry. If I come back here, this memory store is encoded in these loops here, which are pinched at the origin. And with this, you can do plenty of things with calculation. Actually, we played a bit with simulation. You can do this system spiking just like a neuron, etc., etc. So it's really a nice playground that we just found. And actually, right now, we would love, again, to see this memory store. And we are working again with André Geim and Radeboya. And actually, they have some first signature of this kind of memory store effects. But this is really ongoing work. And we need to assess the experiments further to be sure that we see that. Now, and the work of Radar and André Geim is seeing that. Now, the second, and I will stop on this nearly, the second challenge is, and I come back to the beginning of the talk, is can we understand this very weird water-carbon interface? Because again, I showed you this experimental result that the carbon nanotubes seems to have low friction at low size and high friction at high size. So the friction decreases with the radius. And this, I told you that there is no classical explanation for that. And so we came back on this problem from we were thinking and that this may be a quantum friction. actually electronic friction. And this, thanks to, I hope you can see this, thanks to Nikita in particular and Anton Roberts, the PhD student of Lydéric Bocquet, my wife. Actually, so for more than 1 year, we looked at this system from a really an electronic friction point of view. So, you know, I mean, there is electronic friction in van der Waals systems. So you have fluctuation-induced friction. Of course, you have van der Waals forces, but also the equivalent in terms of friction. And this friction actually is described by, is well known, and you can find this expression in many reviews. But actually, first we rederive this for the interface between a liquid and a solid surface, so a conducting solid surface. And there, what is key here, of course, is that you, I hope you can see my slide, but you, of course, you have a cutoff. Okay, so maybe okay, I come to this. Yes. Yeah, I come back to this because there is an issue still. And so the key point is that you have a cutoff for high frequencies. So typically, the typical frequencies you can consider are typically kBt over h bar, which is infrared, let's say terahertz, tens of milli electron volts, which is quite small actually. So, but these are typically the excitations that you will find in the water. So then, I mean, this formula is a bit complex. I don't want to discuss it, but basically it says that if you have a spectrum of fluctuation in the water and a spectrum of fluctuation in the solid below, so let's say graphite or graphene, if the two overlaps, so let's say you have this product, then you have friction. That's the point. So basically, you have it's not really a resonance, but you have a condition of matching between the modes of water and the modes of on the solid. And actually, we found that for water, there is such a resonance below the terahertz, and this is the Debye peak. The Debye peak is a collective mode of basically, let's say, between water. Water is basically fluctuating between each other, and you have a bit something like, sometimes it's called optical phonons, that water, I mean, you have collective modes in water which may behave which leads actually experimentally to this so-called Debye peak. Now on the metallic part, so we looked in general at Gelium models or whatever, but also we look more carefully at carbon. And there we found something extremely interesting, that first we have to look at very small excitations, low energy excitation in the tens of milli electron volts. And then you find a very strong difference between graphene and graphite. In graphene, you have a mode, you have plenty of modes which you can calculate exactly. So I took this from a recent review from surface plasmon polariton. And okay, you have surface plasmon, etc., but they are killed. All these plasmons are killed by Landau damping at high wave numbers. But in graphite, this is different actually. You have a low energy surface plasmon, but which is not killed at high wave vector, meaning that this overlap of modes is very strong for graphite, quite low for graphene. And if you put numbers, you find, if I plot numbers on this last graph, you have a high friction for graphite, low friction for graphene, very low friction for graphene. Actually, and now we start to understand that this transition from high radius to low radius is actually a decoupling of layers between the layers of the nanotubes. And so I think we start slowly to understand that this may well be quantum friction, so electronic friction, and due to this matching or let's say, I don't like resonance, but coexistence of modes between water and electronic friction. So I will not say more because we are still working on that, and that's quite. I mean, there are still a few things to check, etc. But I think we start to understand. And just to finish on that, and this is my last slide. Indeed, I mean, here I only showed you the fundamental aspects of this, but indeed, we are really looking for what is called the water energy nexus. Is that indeed, with all these phenomena, you can really use it, and I really insist on that, to make practical applications. And we have already done a few for water separation, for desalination, and so blue energy, I mean, the creating energy from gradient of salt. And actually, we launched an initiative in the spring. I launched an initiative on that, on water energy, gathering people. So, but I just mentioned that because I think as scientists, we in some sense are compelled to propose solutions. So I would be happy. So if anyone is interested to discuss with me about that, because I think it's important to show that there is not only COVID in front of us, and there are some more important stuff. Okay, so with this is my last slide. And I want to mention in particular Alessandro and Antoine, who are my close collaborator for 10 years, working on all these topics. The collaboration with Manchester and with ENS chemistry on some aspects. So thank you very much.
Okay, thank you very much, Lydéric. It was a really, really beautiful talk.